Well, welcome everybody and good afternoon. Thank you so much for joining us today. My name is Megan Knight, and I'm a master's candidate in food systems at the University of Vermont. And along with my co-author, Liliana Batolo, who's a master's candidate in plant and soil science, I'm really excited to share with you today insights from our work on the upcoming 2025 Vermont Climate Assessment chapter on agriculture and food systems. We'll be sharing some of the major climate trends, impacts, and adaptation strategies that agricultural producers are using to respond to increasing climate variability and extreme weather. So we'll begin today with an introduction to the climate assessment, and then we'll proceed through our main climate change drivers and their impacts on agriculture in Vermont. We'll also briefly touch on adaptation strategies before concluding with resources to learn more after this presentation. We should have some time at the end for questions, so please keep that in mind as you're listening. So without further ado, let's jump in.
Alrighty, let's start with a quick overview of the Vermont Climate Assessment itself, why it matters, and how it came together. As a result of increasing global greenhouse gas emissions, the climate is changing. Climate change assessments were created to provide governments and the public with clear, objective scientific data on the state of a planet under these increasingly more rapid changes. They consolidate hundreds and thousands of scientific papers and global data into a single and cohesive summary that can help inform decision-making and advocate for additional resources and funding. Many people are familiar with the IPCC reports that summarize climate change at the global level, or the National Climate Assessment that summarize changes within the US, but those are often too broad for local decision-making. One important goal of the Vermont Climate Assessment is bringing climate science closer to home. The Vermont Climate Assessment translates climate science into state-specific info that is more actionable for producers, policymakers, business owners, and community members. This is the third Vermont Climate Assessment. The first was released in 2014, the second in 2021, and this upcoming assessment will be released this summer. And I like to note that Vermont was actually the first state to produce a state-level climate assessment, and since then, many more states have joined us. We know that climate change is here, and these reports build on this evidence, summarize impacts, and capture how Vermonters are responding. The assessment covers many sectors beyond agriculture, including water resources, infrastructure, forests, recreation, human health, and energy. Each chapter was led by graduate students with support from faculty, staff, and undergraduate researchers. Climate impacts on agriculture interact with each one of these sectors, and finding from some of these groups' work is highlighted in this presentation.
So our work on the chapter included gathering and synthesizing data from a wide range of sources. The chapter is primarily a synthesis of existing research and reporting, but we also conducted some original analyses using climate and agricultural data where gaps existed. The assessment draws from long-term climate data sets, including NOAA weather station records, as well as USDA Census of Agriculture data and other federal and state databases. We also incorporated extensive peer-reviewed research, extension publications, conference proceedings, and reports from organizations working in Vermont. An important goal of the VCA is to connect climate science to the local context and make it salient, specific, and valuable at the state level. So we also included local stories and news coverage and practitioner expertise. This makes the assessment unique to Vermont and more usable compared to national or regional climate assessments, and it provides specific information that hopefully decision makers can actually use. Our chapter also went through extensive review by subject matter experts from UVM Extension, academia, government, and nonprofit organizations. The organizations represented here include groups like UVM Extension, the Vermont Agency of Agriculture, NOFA Vermont, the American Farmland Trust, Farm to Plate, and many others. These conversations, reviews, and feedback opportunities strongly inform the structure of our chapter and our research sources. In addition, it's worth mentioning that the Climate Measurements Center of Excellence at the UVM Gun Institute conducted a needs assessment last summer before we started work on our chapter development. And this assessment included over 100 stakeholders across all of the sectors covered in the climate assessment as a whole. And we use this needs assessment to inform our research agenda and our chapter development. So here's a quick overview of the contents of the entire Agriculture and Food Systems chapter, beginning with our executive summary and key messages, and then moving through biophysical and agricultural sector-specific impacts, after which we discuss economic and social impacts and adaptation strategies, followed by mitigation opportunities, and finally, food systems resilience and transformation. In this presentation today, we'll be focusing on the biophysical and agricultural production-specific impacts and providing a bit of a higher level summary of adaptation strategies. So the primary objective of our chapter specifically is to equip Vermont food system actors with the latest climate science relevant to agriculture and food systems in Vermont. We want the chapter to be able to support informed decision-making at multiple different scales, from farm management to policy development and future research priorities. As we document these climate impacts, we also aim to provide evidence that supports the need for additional investment, technical assistance, and adaptation resources for Vermont's food system.
The key climate drivers are temperature and precipitation. Agriculture is no stranger to uncertainty and the vulnerabilities associated with weather. We'll first talk through how climate change is driving temperature changes and the associated impacts. Then we'll dive into precipitation and the extremes of both temperature and precipitation, specifically flooding and droughts. Analysis on the impacts of climate change relies heavily on data collected through the National Weather Service cooperative stations. Trends in temperature and precipitation were analyzed across the state, pulling data from 14 weather stations. Regional measurements were captured comparing western, southeastern, and northeastern Vermont. These distinctions include western Vermont's proximity to Lake Champlain, southeastern Vermont's exposure to winds from the Atlantic, and higher elevations across the northeastern region's Green Mountain Range. The figure to the right summarizes many of the major climate changes observed across Vermont between 1900 and 2024. And I see someone leaning in to try and see all that data, but don't worry, we'll dive into all of them. The overall sentiment here is Vermont is getting warmer and wetter, and every temperature-related metric is moving in the direction we would expect under a warming climate, including warmer annual temperatures overall, increasing growing season length, increasing winter temperatures, and decreasing snowfall. Average annual precipitation is increasing as well as the number of heavy precipitation days. While these trends are consistent across regions, you can see some regional differences. In purple, looking in some of the temperature-related metrics, you'll see that warming trends tend to be most significant in the southeastern region, and highlighted in yellow shows the western region, which has experienced the greatest impact in precipitation. We will dive more into these findings in the next slides, and this just captures an overview. So let's first discuss temperature changes and its impacts. It's important to highlight, while these changes are experienced across the US, the Northeast is getting warmer at a faster rate. This graph has the average annual temperatures plotted for the whole nation in green and the Northeast specifically in blue. Visually, you can see a steeper trend line in the Northeast as it is warming faster than the national average. Since the 1900s, the Northeast has warmed roughly twice as fast as the US overall. And when we compare the most recent 30-year period to the earliest 30-year period from 1900, the average annual temperature has changed by 2.69 degrees Fahrenheit, which is nearly 18 times greater than the change observed nationally. Warming temperatures are shifting first and last freeze dates. This figure shows that the last spring freeze is occurring earlier and the first fall freeze is occurring later. And more recently, that divergence is clear, as you can see in that darker grayed out region. And to orient you, the blue line represents the last freeze in the spring, while the red line represents the first freeze in the fall. A downward trend, as shown by the spring freeze line, indicates a shift earlier in the calendar year, which is not as intuitive when reading this, while an upward trend in the fall freeze line indicates a shift later. It's important to call out the interannual variability you see from the noise in the data. Even though the long-term trend points towards earlier springs and later falls, year-to-year variability remains high, especially in the most recent 30-year period for the last spring freeze. Farmers should exercise caution when changing their management schedules in response to spring freeze timing, but this trend is projected to continue and may become more distinct in the coming years. And now when we look at the combined effects of an earlier spring freeze and a later fall freeze, it is clear that the growing season is lengthening. The growing season is now 3 weeks longer than the earlier 20th century, and the rate of change is accelerating, which is especially pronounced in the past 65 years, which you can see in that darker dotted line. One major opportunity with a lengthening growing season is the increased viability of longer season and heat-tolerant crops. As the growing season expands, producers may have more flexibility to experiment with crops or varieties that have historically struggled in Vermont's shorter and cooler climate. In some systems, a longer freeze-free period may also increase productivity or allow for practices like double cropping or longer grazing seasons. At the same time, earlier spring conditions may create pressure to plant earlier. But as I mentioned, producers still need to remain cautious because interannual variability remains high. A warm early spring does not eliminate the possibility of damaging late frost events, and those spring swings can create major risks for certain crops. Warmer temperatures are also expected to increase weed, insect pest, and disease pressures. Milder winters can improve overwinter survival for certain pests and pathogens, while longer growing season may allow some species to expand their geographic range or complete an additional life cycle during the season. So overall, warming temperatures create new opportunities, but they also increase uncertainty and management complexity for producers.
So building on what Lily just shared, one of the important results of climate warming in Vermont can be observed in the shift in USDA plant hardiness zones across the state. Hardiness zones are the standard by which gardeners and growers can determine which perennial plants are most likely to thrive at a given location. Here, we present a comparison of the 2012 hardiness zone map shown on the left and the updated 2023 map on the right. What we can see here is that Vermont's coldest hardiness zone, which is zone 3B in darkest blue on the map on the left, has completely disappeared. And at the same time, warmer zones have expanded northward, and a new warmest zone, 6A in yellow, now appears in southeastern Vermont. Most of the state is now classified as zone 5A. These changes reflect increasing minimum winter temperatures, which can create new opportunities for perennial crops that previously may not have thrived in Vermont. For example, some producers are now experimenting with crops like peaches and other warm climate fruit varieties or species. At the same time, these opportunities come with some challenges and increased uncertainty, as Lily mentioned, especially in the spring when early warm periods could trigger premature bud break, leaving plants vulnerable to late frosts. Next, we'll shift to talk about the maple sugaring season. We created this figure using USDA National Agricultural Statistics Service annual maple producer survey data, which collects self-reported production information directly from maple producers. The figure shows changes in maple sugaring season timing in Vermont from 1963 through 2022. On the vertical axis, earlier calendar dates appear lower and later dates higher. The blue data points and trend line represent the average season start date, while the yellow represents the average season end date in a given year. Our analysis shows, consistent with our reviewed literature on maple production and climate, that both the start and end of maple sugaring season are shifting earlier in the calendar year over time. The reported average season start dates have advanced by approximately 2.2 days per decade during this period, while season end dates have shifted by about 1.5 days per decade. Interestingly, we did not find a statistically significant change in total season length. So, to summarize, maple sugaring season is shifting earlier, but not becoming significantly shorter. So, what does that mean for our state's maple producers? They will have to adapt to this earlier start and end to maple sugaring. They might need to tap earlier, monitor conditions more closely, and adapt equipment and labor schedules to keep pace with a changing sap run timing. However, our research suggests that producers can still maintain overall productivity and sap yields as long as they can shift their operations concurrently with the changing production period. We're going to shift gears again a little bit to talk about livestock and dairy production. This figure shows projected increase in livestock heat stress up to the year 2100 under a high emission scenario, with Montpelier, Vermont shown on the lowest line there in dark blue. Heat stress is commonly estimated using the temperature humidity index. Once this index exceeds about 70, livestock, including dairy and meat cattle, begin experiencing physiological stress. Historically, locations like Montpelier averaged fewer than 20 heat stress days per year. However, with continued high greenhouse gas emissions, projections suggest that could exceed 80 days annually by the end of the century. This represents a major shift for a state where livestock systems are adapted to relatively cool conditions. Increasing heat stress has important implications for Vermont livestock and dairy systems. For dairy cattle, heat stress is associated with reduced milk production, reduced milk quality, lower reproductive performance, and reduced calving success. Heat stress can also suppress immune function, making animals more vulnerable to infections and disease, especially in warm and humid barn environments. In beef cattle production systems, heat stress can negatively affect weight gain and meat quality. These impacts are particularly important in Vermont because dairy remains such a central part of the state's agricultural economy and landscape. So, to summarize our agricultural impacts related to warming temperatures, we have increasing heat stress in livestock, potentially resulting in reduced milk production. In crop production, a longer growing season may create opportunities for increased productivity and success of new crop varieties. However, we could see reduced quality in cool season crops and greater weed and insect pest pressures. We are seeing an earlier maple sugaring season, and in fruit production, the viability of new varieties with the potential for increased frost damage linked to earlier bud break. So overall, as you can see, warming creates both opportunities and vulnerabilities, and adaptation planning will be critical for managing this increasing uncertainty.
Now we'll jump into precipitation. Average annual precipitation is increasing 15 times faster in the Northeast than the US overall. This graph shows that the average monthly precipitation across the US in green and the Northeast, again shown in blue, between the 1900s and 2024. And when we look at Vermont specifically, there's a clear long-term trend towards wetter conditions. This plot shows the average annual precipitation per decade in comparison to a long-term average, which is that line in the middle of 40 inches per year. Since the early 1900s, the average annual precipitation has increased from roughly 36 inches per year to now more than 43 inches per year, representing a 20% increase statewide. Seasonal shifts in precipitation are especially important for agriculture because timing matters just as much as total rainfall. So while an earlier last spring frost may appear beneficial by potentially extending the growing season, projections suggest that springs are also expected to become wetter. Now, this figure shows projected precipitation during the 3 weeks leading up to the last spring frost, represented by the green bars, alongside a shift toward an earlier late frost date, as we discussed, which is shown by the black line. Together, these trends highlight a growing challenge for producers. Farmers may want to plant earlier to take advantage of a longer growing season, but wetter spring soils can limit field access, delay planting, and increase risk of soil compaction. And that creates a difficult management trade-off. Entering fields too early under wet conditions can damage soil structure and reduce long-term productivity, while delaying planting may shorten market opportunities and reduce yields for some crops. Increased precipitation is expected to increase surface runoff and erosion, which can reduce valuable topsoil and increase nutrient losses from agriculture fields into nearby freshwater systems. Wetter conditions combined with management pressures such as machinery traffic and livestock grazing on saturated soils can also increase soil compaction, further reducing infiltration, restricting root growth, and damaging the overall soil structure. These wetter conditions may delay field operations, pasture access, and hay harvests, while also reducing the number of workable field days during the growing season. For many producers, as mentioned, timing is critical, so repeated delays can affect crop quality, yields, and overall farm productivity. Increased moisture is also expected to intensify pest and disease pressures. Many plant pathogens and fungal diseases thrive under warm and humid conditions.
Next, we'll talk specifically about the shifts in precipitation during the winter. So what we have here is a comparison between snowfall and total winter precipitation across those three regions in Vermont. The first three columns are the trends across three 30-year periods over the last 90 years. And in this upper left quadrant, we see a strong decreasing trend in winter snowfall in the last 60 years and especially in the last 30 years. In the bottom left quadrant, we can see, however, that winter precipitation is overall increasing in each 30-year span. So slightly more precipitation, but significantly less falling as snow. In the upper right, we can see the total change in snowfall in inches per decade. So, for example, on the top line in the far right, we can see that the whole state on average is seeing about 24 less inches of winter snowfall since just 1990. And then finally, in the bottom right, here you can see the state overall is seeing about a half an inch more precipitation in the winter in the last 30-year period, with some variation between regions. So again, to summarize, we're seeing more winter precipitation overall, but a lot less falling as snow. This shift matters because snowpack functions as a natural water storage system. Snow accumulates through the winter and then gradually releases water during spring melt. When more precipitation falls as rain, water moves through the landscape much more quickly, which changes stream flow dynamics, increases runoff risk, changes soil moisture content, and can contribute to flooding and erosion. Reduced snow cover also has implications for plant health. Snow cover can provide insulation for perennial crops and soils during winter, and with less snow cover, plants may be more vulnerable to winter cold injury and ice encasement. So overall, increasing precipitation and heavier rainfall events are contributing to several interconnected challenges. For livestock operations, wetter conditions can increase pasture compaction, potentially increase disease and pathogen pressure, and create additional manure management challenges as water moves more quickly across the landscape. For fruit and crop production, these impacts include delayed planting and harvesting, fewer workable field days, increased soil compaction and erosion, nutrient losses, and potential for reduced nutrient uptake, as well as crop damage and disease pressure. Many of these impacts are closely tied to soil health and water management, which is why these emerge repeatedly as important adaptation priorities throughout the chapter. Up until this point, we've mostly discussed long-term trends in temperature and precipitation, as well as shifting seasonality. But for many producers, the most immediate and disruptive climate impacts come from extreme and acute weather events. Vermont agriculture is increasingly experiencing disasters like floods, droughts, heat waves, and freeze events, sometimes all within the same growing season or the same year. These events create not only direct production losses, but also major economic, emotional, and logistical challenges for producers and food system businesses. This slide will highlight several recent climate disasters that had major impacts on Vermont agriculture and food systems. In 2023, Vermont experienced a damaging late spring freeze, which caused particularly severe impacts for orchards and vineyards. Estimated losses include roughly $10 million in orchard damages and $1.2 million in vineyard losses. Many of these surveyed producers reported losing up to 95% of their expected seasonal revenue. Then, Vermont experienced a major flooding event in 2023 and again in 2024. Voluntary survey data collected after those floods shows that surveyed producers lost at least a quarter of their annual income in both of those years consecutively, and most expected negative cash flow following the disasters. Last year, in 2025, we saw again flooding events and a significant drought, which we'll touch on more momentarily. The broader economic ripple effects extend well beyond farms themselves. For example, the total estimated agricultural losses from extreme events in 2023 alone reached approximately $44.6 million across the whole state, while overall food system impacts were estimated at nearly $70 million. An important point highlighted in the chapter and that we want to make clear here is that Vermont still lacks a comprehensive system for tracking climate-related agricultural losses. Unlike some large commodity producing states, the majority of Vermont farmers are not covered by federal crop insurance programs or many insurance programs at all. As a result, both the voluntary state survey data and national data sets likely underestimate the true economic burden that climate change is placing on Vermont's producers. We did also want to highlight specifically this trend of compounding climate stress, where producers face multiple extreme events back to back, either in consecutive years or even within the same season, which leaves them little time to recover between disasters. The feed and forage sector highlights this clearly, with survey results from 2023, 24, and 25 showing impacts associated with recent consecutive floods and drought. Following the 2023 and 2024 flood events, many surveyed producers anticipated feed shortages or declines in feed quality. Then, in 2025, Vermont experienced a severe flash drought that further stressed forage systems, with more than half of surveyed respondents reporting feed shortages and many reporting having to buy supplemental feed. Over a quarter of respondents reported reduced livestock productivity as well. Through this example, we can see how climate-related disruptions can compound across years and create ripple effects from feed availability to livestock productivity and potentially extending to farm viability and regional food supply chains. It's worth noting that when we talk about climate resilience, we should look beyond recovery from these individual events and ensure that farms and food businesses can remain viable under repeated and increasing disruptions.
And so when we dig into the data, we can see that heavy precipitation events are becoming more frequent across Vermont. This figure shows that the decadal average number of days per year with more than 1 inch of precipitation. And since the 1900s, the average annual number of heavy precipitation days has increased by roughly 40%, highlighting a long-term shift towards wetter and more intense rainfall events. However, the trend became less consistent over the last 35 years, likely reflecting greater year-to-year variability and the growing influence of even more extreme events. In many ways, the last 5 years are categorized more by precipitation extremes than gradual trends alone. For example, 2024 recorded the highest average number of days with more than 4 inches of rain at 0.78 days per year. While the total number of days in 2024 with more than 1 inch of rain was not exceptionally high, the year was disproportionately defined by a small number of very intense storm events. Another way to understand the impacts of extreme precipitation events is looking at the stream gauges. This graph compares stream flow data across the most recent 30 years and the years 30 years prior to that. The bar represents the change in the number of days per year where sites experience abnormal, severe, and exceptional high flow events. The stars over the bar indicates whether change is significant. 100% of the sites exhibited an increase in abnormal high flow events. 88% exhibited an increase in severe flow events, and 76% exhibited an increase in exceptionally high flow events. Streams with significant increases are now experiencing 9.4 more days of abnormal flooding and 5 more days of severe flooding in the last 30 years, from 1996 through to 2025, compared to the 30 years prior, 1966 to 1995. Following heavy precipitation and major flood events, the impacts of excess water become more severe and longer lasting. Saturated soils and standing water can delay replanting, preventing field access for extended periods, and increase the risk of soil compaction as producers attempt recovery operations. Heavy rainfall and flooding can strip away topsoil, deposit sediment and debris, and accelerate nutrient losses into nearby waterways, reducing both soil productivity and water quality. Flooding and intense rainfall can also accelerate erosion processes, beginning with sheet and rill erosion, and under more severe conditions, progressing into gully erosion. Prolonged wet conditions also heighten the risk of crop diseases, pest outbreaks, and forage quality losses, while damage to roads, stream banks, and farm infrastructure can disrupt operations and market access long after floodwaters recede. And speaking of market access, in addition to the on-farm impacts of flooding, flood events can severely disrupt food distribution and food access across Vermont. To better understand these risks, we mapped flood-prone areas using both the Lake Champlain floodplain and FEMA 100-year flood zone maps, then overlaid key food distribution centers, including food hubs, independent grocery stores, large grocery stores, and wholesale distributors. The zoomed-in maps of Hardwick, Barrie, and Montpelier highlight how vulnerable food access and distribution networks can become during major flood events. Now, this map is interactive and now publicly available online for further exploration. So if your grocery store is missing, definitely reach out. And while it's not comprehensive, it provides an important starting point for future research, particularly because this analysis does not yet account for factors such as building elevation or site-specific flood protection measures that may influence actual risk. And if any folks are listening from the Ludlow area, you are well aware of the floods that closed the Shaws the summer of 2023 and didn't reopen until December 2024. It was the only grocery store in a half-hour radius, and the flood severely impacted food access for that area for over a year. Similar to the analysis of high flow events, changes in the average annual number of extreme low flow days were calculated using stream flow records across Vermont. Again, comparing the most recent 30-year period to the preceding 30-year period. Unlike high flow events, drought conditions were only classified as low flow events when the stream flow remained below abnormal, severe, or exceptional drought thresholds for at least 7 consecutive days. When comparing the two time periods, 20% of the monitoring sites exhibited an increase in abnormal drought days, 28% showed an increase in severe drought conditions, and 88% showed an increase in exceptional drought conditions. While statistical significance was limited across all 3 drought categories, meaning some observed increases may be attributed to natural variability, these trends highlight the importance of continued monitoring as climate change is expected to increase the frequency and severity of prolonged low flow conditions in the future. The recent June to October 2025 drought that plagued Vermont is a reminder that flash droughts can be especially damaging for agriculture because they develop rapidly, often leaving little time for preparation or adaptation. While May 2025 was nearly 50% wetter than the long-term average, conditions shifted dramatically over the summer, with July through September experiencing substantially below average precipitation. The drought began intensifying in July, which was 56% drier than the long-term average, followed by an August that was over 70% drier than normal, and September that remained more than 30% below average precipitation. These rapid shifts from wet to extremely dry conditions created significant stress for crops and forage systems, already recovering from earlier excessive moisture. By mid-September 2025, 100% of Vermont was experiencing some level of drought conditions, making it the most severe statewide drought ever recorded since 2000. The drought reached its peak on October 14th, 2025, as you can see the map on the left, when 67% of the state was classified under extreme drought conditions, shown in red on the left map, with northeastern and central Vermont impacted most severely. The map on the right shows conditions just 1 month later on November 18th, 2025, when precipitation and cooler temperatures began easing drought intensity across the state. Although conditions improved significantly, portions of Vermont still remained under severe and moderate drought classifications, highlighting how prolonged drought impacts can persist even after rainfall returns. Drought risk is exacerbated by longer freeze-free seasons that increase evapotranspiration and by increasing erratic summer precipitation patterns. Within a single growing season, farmers are increasingly experiencing the whiplash of climate extremes, where periods of excessive rainfall are followed by extended dry conditions with little recovery time in between. These drought conditions increase plant water stress, limiting crop growth and reducing productivity. Prolonged dry periods can also contribute to crop losses, lower forage quality and yields, and create increasingly unreliable water availability for both crops and livestock. Extreme flooding and droughts can have a devastating impact on agricultural production, and farmers will need to continue investing in adaptation strategies, which Megan will discuss shortly. Some farming systems have struggled to recover from repeated climate extremes, while others have relied heavily on recovery assistance from government programs, nonprofit organizations, or community crowdfunding efforts. However, adaptation cannot fall solely on farmers. Before many producers are able to invest in long-term resilience strategies, basic needs such as affordable healthcare, childcare, stable labor, and financial security must also be addressed. While not covered and detailed in this presentation, the Vermont Climate Assessment highlights many of the ways farmers, communities, organizations, and policymakers across Vermont are working to address these challenges and strengthen the food system resilience.
Now that we've covered all of those impacts from warming temperatures to increasing precipitation and more severe acute weather events, we have just a brief moment to highlight adaptation pathways. The purpose of our discussion of adaptation strategies, both here and in the full chapter, is not to prescribe specific actions, but to document what we're seeing producers and food systems actors doing on the ground. Adaptation is very much already happening in Vermont with farmers, researchers, extension professionals, and community organizations all implementing strategies to improve food systems adaptability and long-term resilience. To that end, we wanted to highlight several broad adaptation strategies that emerged repeatedly across the literature. Improving soil health was one of the most commonly discussed strategies, which can help improve crop resilience to flooding and drought. Water management was another major theme, along with diversification. Diversification plays an important role in adaptation and resilience, both at the farm level and across the food system. Many producers are also investing in infrastructure and equipment that helps them adapt to new climate normals or new production strategies. And they're using techniques like integrated pest management and agroforestry as well. A key point here is that adaptation strategies are highly context specific, and what works for one farm may not work for another, depending on multiple factors like soils, topography, the type of enterprise and crops grown, labor availability, and financial capacity. This slide goes into a little bit more detail on adaptation strategies according to the main climate drivers. For excess moisture, flooding, and water management, we see strategies that include tile drainage, field grading, and riparian buffers. Some farms are also converting highly vulnerable land to perennial crop cover or adjusting crop placement based on flood exposure. For drought and water stress, adaptation strategies focus heavily on improving water access and water use efficiency. Examples include drip irrigation systems, on-farm water storage, and soil health practices that improve moisture retention. For warming and heat stress, livestock farms might invest in ventilation systems or cooling technologies like misters. Crop producers may use shade cloth, heat-tolerant crop varieties, frost protection systems, and delayed bud break varieties for orchards, as well as altered planting schedules. Maple producers are also adapting through technologies like vacuum tubing systems that can increase and maintain production with more variable sap float periods. Another important point here is that many adaptation strategies also provide co-benefits and can support broader goals around productivity, sustainability, ecosystem function, and farm viability. In addition to production system adaptations, as Lily mentioned, broader economic and social support systems are key to continued farm viability in the face of a changing climate. In closing, climate change, including warming temperatures, increasing precipitation, and increasing severe weather events, poses significant risks and challenges for Vermont agriculture and food systems. But it also creates opportunities for innovation, collaboration, and transformation. One encouraging takeaway from this work is that Vermont already has strong community networks, a vibrant local food movement, and deep agricultural knowledge that can support adaptation. Long-term resilience will require continued investment in research, technical assistance, infrastructure, disaster recovery systems, and policies that support producers through increasing climate uncertainty. We'll briefly touch on some more resources to learn more about the climate assessment before moving into our Q&A time.
Well, we covered a lot of doom and gloom in this presentation. There is ever an increasing amount of resources created by and for the agriculture community in Vermont to increase resilience, adapt, and mitigate climate change impacts. Those resources include the soon to be released Vermont Climate Assessment, which will be shared through this link later this summer, along with prior editions already available on the site. This presentation is also available upon request, so please feel free to email either of us. The shared version includes the speaker notes and full figure captions for additional context. For those looking for a shorter summary, UVM Extension recently published a 2-page overview highlighting key findings and implications for Vermont agriculture. And also recently released is the Climate Adaptation Resources for Farmers website, which was developed in collaboration between the University of Vermont, the University of Maine, and the American Farmland Trust. The site compiles research and practical guidance on climate adaptation strategies most relevant to Vermont ag. The USDA Northeast Climate Hub also provides a wide range of additional tools, research summaries, and decision support resources. Finally, of course, local UVM Extension offices remain available to support farmers, producers, and communities navigating climate-related challenges. So stay tuned on the assessment release, and thank you so much for joining us as we share some highlights specific to agriculture production.
Yeah, thank you all so much for your attention to our presentation today. We want to acknowledge the many collaborators, reviewers, and community partners who contributed to the Vermont Climate Assessment and specifically the Agriculture and Food Systems chapter. This work was highly collaborative and a huge learning experience for both me and Liliana as graduate students. And it would not have been possible without contributions from experts and organizations across the state, fellow chapter co-authors, and our amazing, wonderful leadership at the UVM Climate Measurements Center of Excellence. So with that, that's the conclusion of our presentation, and we're more than happy to stick around for any questions, comments, discussions that you all want to have. So thank you again. I'll take a look in the chat to see if you don't want to speak your question out loud, you're more than welcome to type it into the chat as well, and we can read it out.
Hey, I had a question.
Hey, Kara. Yeah, go ahead.
You guys did a really great job. I enjoyed learning about the assessment. I was wondering if you considered wildfire and wildfire smoke in your assessment.
Yes, yeah, we did. So that was part of one of the sections that we didn't touch fully on in this presentation. That's actually under our social impacts and adaptation strategies around farmer and farm worker health and safety. We refer heavily to the human health chapter in terms of the actual wildfire smoke and analysis, but it is an increasing workplace safety threat that farmers and farm workers face in Vermont. And we are experiencing, I don't have the statistics totally memorized, but we are experiencing more wildfire smoke in Vermont than previously. So we do talk a little bit about some of the adaptation strategies can be improved PPE or taking certain times or days off when there's increased wildfire smoke to protect people's lungs and well-being. So that's a great question. Yeah. Alex, I see your hand is up. Go ahead.
Okay, fine. I'll swallow my snacks.
Sorry.
Thank you. I've tried to look up some of this data. It's rough. You got to know what you're doing. I looked up that same data as you did on events with more than 1 inch rain per day. And it's just super hard to A, locate the stuff, B, like what's missing, and C, like how are they even finding things? Like, is a day 24 hours or is a day a calendar day? Like you could have more 24-hour events than you could have day events because the 1 inch happened during, it's all just like, wow. So on that note, I want to know, like, this is a little bizarre, but you showed on the very first slide the graph of the Vermont flooding. And I am a very big fan of hydrographs, along with my 10-year-old son. And what was really fantastic or abysmal, depending on how you think about it, for the Montpelier, is that the prediction was not what that graph said.
Hmm.
So it was like a fake out. Like the actual graph was like a pump fake in basketball. The graph went up like this. The prediction said, okay, we're done. And then actually, no, we're not done. Boom. We have like, high action level. So it sucked. And
Hmm.
I didn't personally get hammered by that flood, but a lot of people here did in Montpelier,
Oh,
where I live. So I'm wondering, like, is that prediction data available in a way that it can be compared to what actually happens? Because maybe the more extreme of the event, the less correlation there is. But yeah, it wasn't pleasant.
sorry, I'm bouncing around everywhere.
Sure. Anyhow, just something to,
You're
to
talking
think
about this
about. I'm
one?
just sort of halfway complaining, but it's like, where do you find that data? Can you compare what they're saying to what really happens?
Mm-hmm. Yeah, it's a really interesting question. I don't know if there's a particular source for the comparison between flood projections and sort of the post analysis of data after a flood event, but it's a really good point because I think we need to be adjusting our predictions. I think was it the red bar chart of stream flow
No,
flooding
the
that
very,
you're
very, 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 very
the
first
very
slide.
first one. Okay, yeah, the summary.
Sorry.
Yeah. No,
Yeah,
it's a good
no, I mean,
point.
it's like that first slide where you're introducing the whole thing, and on the left is the Montpelier graph.
Yeah.
I mean, you don't even have to say it's a Montpelier graph. I recognize that graph.
Here with the
No, no,
oh,
earlier slide on the hydrograph, the water height.
maybe it was the stream flow. Either way,
There it is. There it is. There it is. Primary data right there.
oh, okay. I see what
Oh,
you mean.
oh, from
Yeah.
yes.
Yeah, that
Yep.
that graph,
Yep.
right? So we were, the difference between action level and then major is only
Hmm.
like 2 feet.
Hmm.
So when they told us we weren't going to hit major, okay, but then we did,
Mm. Yeah.
by like 3 feet.
Hmm. I think it's a really good example of how important accurate information is to our response to disasters.
And
And
what do
that's
you do if you're a
something,
farmer? You're
yeah,
you're looking at these tools.
yeah, absolutely. And it's something actually, I think if I maybe a slight digression, but something that Lily and I grappled with a lot throughout writing this chapter is that agriculture, I think, is such a unique, agriculture and food systems are such a unique system in that there's so much human management. So our impact is not just whether the stream reaches a certain height and whether the field is flooded or not. It's about what crop was lost, what was done after the disaster, like how long did that field stay out of production? Like there are so many management challenges. Was the farmer able to prepare? Did they have 30 minutes notice? Did they have 24 hours notice? There are so many human factors that really do depend on accurate prediction information and accurate information for farmers about what to do to recover. So, I don't have all the answers by any means, but it is the human factors are so important. And that's why I mean, we are doing a really good job, I think, as a state in giving farmers a lot of information and resources, but there's always more to seek out there. So hopefully the climate assessment is one small piece in the puzzle of giving people the information they need to support climate change decision making.
Yeah, and there's also a lot of variability within Vermont's
Yeah.
topography too. And so this, I think, was the first year that we broke it out into these different regions. And so even more so, like there's even more monitoring stations that we could have included. And they're in the report, they did look at some of the elevation differences too. So I think that the specificity is slowly being layered on, but yeah, it's a pretty
Mhm.
diverse landscape, so can make it challenging from area to area for predicting.
Yes.
I don't know if that answers your question, Alex, or
No,
if there was a
it's great.
question.
I
I
like
mean,
that.
I'm trying to
Yeah.
find you the hydrographs of the prediction, which I thought I did a snapshot of versus the reality.
Yeah,
Mhm.
And I think I might, I can't find it. Sorry. But
no
yeah,
problem.
they did data, right? There's data that they used to make a graph of a prediction.
Hmm.
How does it stack up?
Hmm. I like that you picked up on a figure that wasn't even a highlighted figure. I appreciate that attention to detail.
Well, I guess we're all a little traumatized over here in Montpelier.
Yeah.
Understandably so. Yeah. Other questions, comments, discussion points even? Yeah,
I have
we're happy.
a quick question.
Yeah, please go ahead.
Are y'all thinking about putting together any kind of like poster or flyer, some kind of short, punchy, synthetic, this is the latest data for Vermont farmers that is a little bit easier to hand out?
Totally. UVM extension, Molly is on the call. She led this, kind of taking findings from the report and made a 2-pager, which is linked in the resources here. Sorry, I really hope this
I
is
can
not...
also drop it. I'll drop it in the chat.
Yeah.
Drop the
That'd
link.
be awesome.
Yeah.
Thanks so much. Sorry if you guys already said that.
No,
that's
no problem.
okay. And then the chapter itself has an executive summary, and there will be released along with the chapter like a 2-page policy brief type of material too. So we, in addition to the UVM 2-pager, which I think focuses a lot more on the data, if folks are looking for a shorter summary of the chapter, the climate assessment itself, some of those materials will be available when the report's actually released later this summer. That's a great question. We want to make the information as accessible as possible.
That being said, though, we did make these slides ones that people can use. And so tried to write key takeaways on each of them and have the notes. And so if there's any of these slides that you'd love to bring in a conversation, I think our biggest goal is to get this data out there so that it can be used to help get more funding opportunities and get people engaged with it. So yeah, if you send us an email, we're happy to send you this presentation and feel free to use as needed.
Other questions, thoughts, surprises? Hopefully there are no surprises. Alex, yeah, sure, go ahead.
So when you had this freeze date thing, I mean, I think I put up an emoticon when I saw that, because the USDA zone map is like, that's what everyone wants to know, right? What zone am I in? What can I plant? And to see the change in that is really just fascinating and insightful for me. I was wondering about, there's talk, at least in the farming community, about the variability on freeze dates. And there's that whole graph you had, but none of your trend lines have a standard deviation or a plus or a minus. Like you talked about variability, but people say stuff like, well, we never know when the spring frost is going to come, and like, is there some way to check that? Like, is the variability on the last spring frost getting higher?
So I totally nerded out about this during it because I was like, I'm curious if it has become more variable. And so I plotted the change in standard deviation over time for both the growing season length and the first and last freeze dates. And there's a couple things happening. It's like when monitoring stations come online, definitely like influence it. So I also tried to reduce it to the stations where we have the full year of data. And there was no significant change in variability. It's been pretty consistently variable. So that was the key finding there. And that is included in the report, some of that. And also, if you want to email me separately, I'm happy to kind of share details of that analysis too. But I also was kind of curious about that, especially when talking with Heather Darby. She was very much like, now don't go telling people earlier spring freeze means that they can plant earlier. Just you're still seeing a lot of variability. So, and that's clear, but the data isn't showing that more variability is happening. Yeah.
That's a great question, Alex. Thank you.
I'm so glad you asked.
Don't encourage me, because I'm going to ask another one. So, ditto sugaring, like are there fewer good sugaring days? Not that that's a definable weather thing, but like I watch it because I got the backyard buckets, and you'd have to have a lot of data, but you have your ideal sugaring days that come in a row, and then you get a good run. Is that less and less happening? I don't know the answer to that, but there's another little nerdy thing that I was
Yeah.
wondering about.
Yeah, that's a really excellent question.
Oh, stop with that. Stop with that.
Sorry.
My head is going like this.
That's a moderately interesting question. No, I'm kidding.
Thank you. That's better.
I think so. The maple sugaring is really interesting, and we of course go into a lot more detail in the chapter. So our analysis doesn't extend into the level of detail of like within the sap flow period, like strings of days that are good sap runs or not. However, it's really interesting in maple, this sort of there's two things happening. One is that sap flow is a pretty complex function of like the tree physiology. So there are other factors besides long-term climate trends that determine the sap flow period in the trees. That was a whole area of research that we had
Yeah.
to broach. So actually in a really similar vein to first and last freeze dates, there is still a lot of interannual variability, and you can see that in the graph when you go to look at it. However, there's the strong trend of the sap flow period as a block shifting earlier in the season. So same length, but the average start, average end date. And I do want to caveat that particular graph is producer survey data. So it is voluntary survey data conducted by the USDA Agricultural Statistics Service. So it's not necessarily representative of the entire state or anything like a census, but it is a pretty strong indication of how we're seeing that sap flow. And it's consistent with other literature around the state and the region as well. The other interesting piece of maple sugaring is that there has been so much technological advancement in the last several decades in terms of vacuum tubing and many other technologies that are able to preserve and increase sap yield and quality during the sap flow period. So we almost see technology as like a buffer against what could be some of the impacts of climate on the sugaring industry, if that makes sense. So there's definitely more room for research there. I know the Proctor Maple Research Center is doing a lot of work, but it was kind of an interesting juxtaposition to say like, wow, there's this huge shift earlier in the year, but not a lot of impact on the actual sap and subsequent maple production. Yeah, if you look at maple production, it's much more tied to sort of interannual variability than it is to long-term climate trends. So yeah, hopefully that answers your question. Yeah.
Well, we're at 3 p.m. Our emails are up here. Please feel free to reach out with any more questions. And if you'd like this deck, I'm happy to share it. Yeah, and thank you so much for taking the time out of your day to